Hi students, welcome to the video session on multipole expansion, potentials at large distances. This video is a part of MSc for semester 1 electrodynamics. We all familiar with electric potentials. The electrostatic potential due to a single charge is given by V equal to 1 over 4 pi epsilon naught Q over R. Now, what if you consider a system of charges? You consider a system of charges, or we can call it as a localized charge distribution. So, at a very large distance from this localized charge distribution, you can consider this as a single charge with a charge Q. And therefore, the potential can be V equal to 1 over 4 pi epsilon 0 Q over R. Just you have to remember that we are talking about the potential at large distances. So only at large distance this V is equal to 1 over 4 pi epsilon 0 Q over R. But what if the total charge is 0, or if the distance is not, if you consider the contribution from each charges, if the total charge of this localized charge distribution is 0, then we have to say the potential is 0 as per our expression that we wrote previously. That means if due to a localized charge distribution, potential V is equal to 1 by 4 pi epsilon 0 Q over R. Because we are not considering the contributions from individual charges, and we took only one distance from the total charges, but actually it is not R only, because from Q1 the distance is R1, from Q2 the distance is R2. So like that the distance are varying. Also the charge contributions are also different. So the assumption that we took, the localized charge distribution, like a single charge, it is we have to extend that, or that is not completely true in some cases. So that is why we are going to use what is called a multipole expansion to find approximate potentials at large distances. So before going to the application of this multipole expansion, let us consider what we already learned about potentials due to an electric dipole. What is an electric dipole? An electric dipole is a system of two charges of equal magnitude but opposite polarity. And you can find such a dipole in this figure, having charges plus q and minus q separated by distance d. And we need to find the potential at a point distant r from the center of this dipole. So as we know, the total potential at that point V will be the sum of V positive plus V negative. V positive is the contribution due to the positive charge, and V minus is the contribution from the negative charge. Therefore, the total potential is V plus plus V minus. Now we can substitute the expression for potential due to single charge. What is that? 1 over 4 pi epsilon 0 Q over R. R plus is the distance from positive charge. Then minus 1 over 4 pi epsilon 0 Q over R minus, where R minus is the distance from negative charge, and it became negative because the second charge is a negative one. So this is the total potential at that point. Now we can simplify this using the law of cosines, and you can see the distance. I'm not going to the elaborate math in this. So the distance 1 over R plus, or 1 over R, can be written as, what is 1 over R? 1 over R is 1. This is a cursive R. 1 over cursive R equal to 1 over R times 1 plus or minus d over R cos theta to the power, or root of to the power minus 1 by 2. Okay, that we can approximate using the binomial theorem. So 1 over cursive R is equal to, or we can expand this, 1 over cursive R plus equal to 1 over R times 1 plus d over 2r cos theta. And similarly 1 over cursive R minus equal to 1 over R times 1 minus d over 2r cos theta. Okay, you can do this math on law of cosines, and you will get the answer like as shown here. Okay. Now, by substituting the r plus 1 over r plus and 1 over r minus in the above equation, so we are plugging in this equation, then this equation will become. So what is 1 over r cursive or minus 1 over cursive or minus? That is equal to, you can see in that 1 over r terms cancel, and d over 2 r cos theta and d over 2 r cos theta, that will become 2 d over r cos theta. So 2 cancels. So that will give 2, sorry, that will give d over r square cos theta. So that can plug into this expression. So we get the expression for potential is equal to 1 over 4 pi epsilon 0 qd cos theta over r square. This is the well-known expression that we studied for potential due to dipole. So we got that expression. Once again, we derived that. So v is equal to 1 over 4 pi epsilon 0 qd over cos theta by r square. So in this, we already know that the potential due to a single charge, it is reduces as 1 by r, but due to a dipole it reduces as 1 by r square. A dipole consists of two charge system, right? So now let us consider here, this is a dipole, and the next one is a quadrupole. A quadrupole is actually a system of two dipoles, and you can see that the potential due to a quadrupole, it reduces as 1 by r cube. And next you can see a system of two quadrupoles, and we call it as an octupole, and there the potential reduces as 1 over r to the power 4, and it goes on. So we derive the expression for dipole, but in the case of quadrupole or octupole, the potential reduces as 1 over r cube and 1 over r to the power 4 respectively. So now we have to find an expression for, or a common expression for, the potential due to a localized charge distribution, whether it is a dipole or a quadrupole or an octupole or even more than that. So we have to get an expression for, a common expression for potential. So for that, that is our aim of this, or this session actually. So here we are describing how multipole expansion is used for finding the potential due to a localized charge distribution. So in the previous example that we showed the expression for potential due to a dipole, and how the potential due to quadrupole and octupole all occurs. Now we are going to get a common expression for all these potential due to any localized charge distribution. So for that, we are taking the expression. So here you can see a localized charge distribution over a volume d tau. So there, and we have to find the potential at a point P. Okay, now, so that potential at that point P can be written as V equal to 1 over 4 pi epsilon 0 integral of rho d tau. What is rho? Rho is the volume charge density, and d tau is the volume element. So here we consider a small volume element d tau dash. So potential is equal to 1 over 4 pi epsilon 0 1 over cursive r times rho d tau. Rho d tau will give the charge. So it's actually the expression for potential due to single charge. So such a large single charges we are considering. So like this, we can consider many small volume elements here that act effectively as a single charges. Okay, so we got an expression here 1 over 4 pi epsilon 0 integral 1 over r rho r dash d tau dash. Now we have to apply the law of cosines for getting the expression for this cursive r as we did in the previous case. So we can write r square equal to r square plus r dash square minus 2r r dash cos theta dash. What is r? You can see in this. Okay, so this is the small volume element that we considered, that is P. That r square can be taken outside as 1 plus the term given here now, and that can be simplified. So r square, this is r square, that will give r equal to, so square root of this term, so square root of this r square will be this term, and this next this entire term is given epsilon here. So cursive r equal to r times root of 1 over epsilon. So okay, the terms here, what are these? R, this is the volume element d tau dash, and from there the distance to this is point P. Okay, and from here we can say this is R, that's effective center of the localized charge distribution. Z, So because this is the localized charge distribution, this is the effective center of that one, that is R. Now there are so many such volume elements. So to one such volume element, the distance from the common center is R dash, and from there to the point P, it is cursive R is the distance. Okay. Now come back. So okay, yeah, this is epsilon. What is epsilon? That is the term given in the bracket other than 1. Okay, so now 1 over, so this is the expression for R. Now we can simplify for 1 over cursive R. So 1 over cursive R will be 1 divided by 1 by R, 1 plus epsilon raised to 1 by 2. That is taken to the top as minus 1 by 2, and we are applying the binomial expansion. So we get expression 1 over R, 1 minus 1 over 2 epsilon plus 3 over 8 epsilon square minus 5 over 16 epsilon cube, etc. So this is after applying the binomial expansion, we are getting this expression. Okay. Now you can simplify again. You can rearrange the values of epsilon. So epsilon is again rearranged or substituted, and we get this expression. So in the binomial expansion, we substitute for the term epsilon, and this is the final expression that we are getting. Or we can write this as 1 over cursive R equal to 1 over R plus times 1 plus R dash by R cos theta dash plus R dash by R square 3 cos square theta dash minus 1 divided by 2 plus all this. So it extends. Okay, only 3 times is 4 times is written here. That can be but after substituting the values, we get the term can be expanded like this. Okay, so 1 over cursive R equal to 1 over R times 1 minus 1 by 2 R dash by R times R dash by R minus 2 cos theta, and so on, so on. So this is the that in from this we can take 1 over R out, and that will give 1 over R is equal, sorry, 1 over R times 1 plus R dash by R cos theta dash R dash by R square 3 cos square theta minus 1 divided by 2. So that is by, you know, the final expression, that is this expression, this one is obtained by clubbing the similar powers of R dash by R. So from this first term, the similar powers of R dash by R can be clubbed, and that yield this expression, this present expression. Now, so this is 1 over R. So this 1 over R expression we can substitute for the expression for potential due to localized charge distribution. So here is the 1 over R. So that will give this expression, that is 1 over 4 pi epsilon 0. 1 over R can be taken outside times first term. You can see the first term is 1. That is why rho d tau. Second term is R dash by R. There is 1 R outside. So that is why 1 over R square times R dash cos theta dash rho d tau. And the third term, you can see it is 1 over, there is 1 R outside and there is 1 R square here. So it is 1 over R cube times R dash square times 3 cos square theta dash minus 1 by 2. 1 by 2 is there. There is all. So 3 by 2 and 1 by 2. Rho d tau dash plus etc. Then the next term, and so you can write the entire term. It extend. Okay, so only first 2-3 terms are explained here. I hope this explanation is clear for. It's only pure mathematical substitution of the term. So first we get the values of this 1 over cursive R, and that is substituted in the expression for potential due to localized charge distribution. And after clubbing all the similar terms with R dash by R, powers of R dash by R. Okay. So this expression we got for potential due to localized charge distribution, you can see that the first term that corresponds to or term with 1 over R, that is the monopole contribution. Then the second one will be 1 over 4 pi epsilon 0, 1 over R square R cos theta dash d. This is the dipole contribution. The next one will be 1 over R cube. So that is the quadrupole contribution, and the next is octupole contribution, and so on. So all these contributions are included in this common expression for potential due to the localized charge distribution at large distances. But at large distances, you know, the first term, that is the monopole term, contributes, and that yields an answer at large distance 1 over 4 pi epsilon 0, 1 over R. What is integral rho d tau? That is the total charge of the contribution. So that is what we obtained the first. Initially, we wrote the total due to a localized charge distribution is 1 over 4 pi epsilon 0, 1 over r or q over r. This is the effective one. But even there are the contribution from the quadrupole term, the octupole term, all these terms are there. But at large distance, we can approximate to the contribution. The dominating contribution is from the first one, or the monopole term. So in the expression for potential due to localized charge distribution, we identified the contribution due to monopole term, then the contribution due to dipole, all this. So here, if the total charge is 0, the dominant term in the potential will be dipole. And so we can write the potential due to dipole as the second term in that, that is 1 by r square term. So 1 over 4 pi epsilon 0, 1 divided by r square integral r dash cos theta dash rho d tau. This is the expression that we pick from the full expression for potential. The second expression with 1 divided by r square is the dipole contribution. The first one was monopole contribution. Okay, now r dash cos theta dash can be written as r cap dot r dash. This is a dot product, a dot b is equal to ab cos theta. So we are using that expression here, and so we can write this potential due to dipole as 1 over 4 pi epsilon 0, 1 divided by r square. Now instead of this r dash cos theta dash, what we wrote is r cap dot r dash, then rho d tau. That terms are there from here. It's the same thing. Okay, so now here we can, this integral term is termed as p is equivalent to integral r dash rho d tau. What is that? R dash is the distance and rho d tau is the charge. So charge times distance, we call it as that the dipole moment term. We have learned the it is the term, the product of charge and distance. R dash here and rho d tau is the charge. Integral rho d tau is the total charge of that. So we got the expression for dipole moment in that. So using that expression, the total potential due to dipole contribution is given by 1 over 4 pi epsilon 0 p dot r dash r cap dot p or p dot r cap, both are same because a dot b is and a dot b and b dot a are same. So we wrote it as v potential due to dipole as 1 divided by 4 pi epsilon 0 p dot r cap divided by r square. Now the term p is actually eliminating the integral. We can write in terms of summation for n number of charge particles. We can write p is equal to sigma I from 1 to n qi ri dash. It was like ri qi. This qi was actually, we wrote as rho d tau in the previous slide that we explained. So r and q, the product of charge and distance, the sum of the products of charge and distance is a dipole moment. Now if there is only two charges for a dipole, okay, so we can write it as q r plus minus q r minus, or q of r minus r plus minus r minus. This is the vector r plus minus vector r minus. That is effectively the distance between the two charges. So that is why it is the term as d. Okay, so that is q times d. This is what we learned in the normal case as a dipole moment is equal to q d. It is due to two single charges. If I localize the dipole system, then it will be the total expression is p is equal to sigma I from 1 to n qi ri dash. So by plugging this expression by plugging this expression for p equal to qd in the expression for v potential dipole p dot r, we can find this p, this is equal to p cos theta, and the p cos theta is actually qd cos theta. This is the common expression that we learned. These are some diagrams of monopole, the dipole, quadrupole and systems. Now let us move to the electric field of a dipole. We have to find the electric field of a dipole. We already learned the electric field of a dipole, but here we are following we calculated the potential due to dipole, and from that we are calculating the electric field of a dipole. So we know that the potential due to dipole is equal to p cos theta over 4 pi epsilon 0 r square. This is just now we described. Also we know that electric field is a gradient of potential. So E is equal to negative dou V divided by R. So that is what we are using here. Okay, so in terms of the polar coordinates, we are using ER, E theta, E phi. So what is that? That is negative dou v by dou r, and that is the next one is 1 over r dou v by dou theta, and 1 over r sine theta dou v by dou phi. So now differentiating this potential with respect to the variables r and theta, we get 2p cos theta by 4 pi epsilon 0 r cube and p sine theta by 4 pi epsilon 0 r cube. So clubbing the total expression for dipole, electric field due to dipole, is p divided by 4 pi epsilon 0 r cube times 2 cos theta plus sine theta. This is the total expression for electric field due to dipole that we derived from potential due to dipole to the electric field. So here you can see the electric field lines due to a pure dipole. The pure dipole consists of only two charges, but you can see the physical dipole, a physical dipole that consists of contributions from quadrupole and octapole, etc. That is the, so you can see both these electric fields shown there. So thank you, students. This is about multipole expansion, potential, and then calculation of electric field due to a dipole. Thank you.